Hello everyone, I am Gonzalo Ferrada, a PhD student at the University of Iowa. In this presentation, I will talk about model simulations and evaluations that we made for Southern Africa in September 2016 using QFET and our custom emission inventory. There are several emission inventories out there and they can be classified according to their method in estimating emissions. The bottom-up approach uses the burnt area, while the top-down approach uses the fire radiative power to estimate emissions. Both rely on remote sensing observations and use emission factors for different species of aerosols and trace gases. Examples of these inventories are GFET and FIN that use the bottom-up approach, while GFAS and QFET use the fire radiative power method. The problem with these inventories, with the exception of FIN, is that they provide gridded emissions that go up to roughly 10-kilometer resolution, which is fine for coarse model simulations. But this is a problem when running high-resolution simulations, since the fires can be misplaced. Also, they offer a limited amount of species, such as hydrocarbons, which play an important role in the formation of secondary organic aerosols and ozone. So we created our own biomass burning emission inventory based on VIRS thermal anomaly detections. We called our emission model as VIRS BBEM. In this model, we are also using the top-down approach to take advantage of the fire radiative power retrievals. Our emissions can be gridded up to 1 kilometer resolution, which is perfect to use in simulation at high resolution, avoiding the misplacement of fires. We are also running the most updated emission factors from ANDRE 2019. This allows us to generate emissions for 36 species, including complex hydrocarbons. In this presentation, I will also discuss the impacts of using the plume rise process in model simulations. The animation here shows the impacts of using this process. This is an example of a fire that occurred in 2019 in Washington state. In the top, we show a cross-section from surface to 10 kilometers, and in the bottom, you see a spatial map at 500 millibars. In the left are the results when we use plume rise, and in the right when it's turned off. You can see that plume rise allows for the development of the plume releasing part of the emissions in the free troposphere that allows for the long-range transport of smoke. On the other hand, when plume rise is turned off, all emissions are released in the surface and then mixed within the boundary layer due to its turbulence, but the plume never reaches higher levels. This process is particularly important when you have large fires and smoke that can be transported miles away from its source. In this study, we will show how this process can alter model simulations in southern Africa. All these developments can sound very good in theory, but we need to evaluate them. The availability of data in the African continent is very limited, but the Oracle's campaign was carried out there from 2016 to 2018. Therefore, this campaign is a perfect opportunity to do these model evaluations using their airborne data. In the animation here, you see a sequence of all the flights conducted with the P-3 aircraft in 2016. In this year, they also had the ER-2 aircraft, which flew at altitudes of around 20 kilometers and provided LiDAR data. We used WorfChem to conduct simulations for the domain that you see in the figure. It has a resolution of 28 kilometers and 56 vertical layers. We fed the model with two reanalysis products from the European Center for Medium-Range Weather Forecasts, ERA5 reanalysis for meteorology, and CAMS reanalysis to account for chemistry and aerosols. We ran 3 sensitivity simulations using the same configurations, except by changing the biomass burning emission inventory and the use of plume rise. We used QFET and our custom emission inventory, and both of these simulations were run using plume rise. Then we made a third simulation with our custom emissions, but turning off plume rise. All simulations were made considering a 17-day spin-up period for chemistry and aerosols, and then we ran until September 15th. We did not run the whole month because of the high computational cost. Also, we applied different diurnal cycles depending on 4 grouped biomes, as you see in the figure, normalized by percent of daily emissions in each model grid box. These diurnal cycles are longitudinal dependent and they have peaks at earlier afternoon. To begin our evaluation, we start by assessing the meteorology of our simulations. Here we are comparing horizontal wind speeds against ERA 5 reanalysis since it provides a representation with no data gaps. In the top, we are showing winds at 700 millibars and in the bottom at 600 millibars. We are considering this level since here is where the mid-level jet responsible for the transport of smoke over the ocean is visible. You can see that the model reproduces it. However, its intensity is slightly overestimated by around 7 kilometers per hour at 600 millibars. We also took atmospheric soundings from St. Helena Island. These are average conditions during September. The SQT log P diagram in the right shows the observations as continuous line and the model in dashed lines. You can see that the model reproduces the air temperature extremely well, with biases in the order of decimals. Also, the relative humidity is very well represented, but with a humid bias in higher levels. Another important aspect for this region is the reproduction of the boundary layer height. If we take the model output that comes out from the boundary layer parameterization, we underestimate the heights by around 700 meters, as you can see in the blue line and the blue dots in the scatter plot. This may be due to the physics of the parameterization itself, which uses the kinetic energy to determine its height. However, if we define the boundary layer height as the maximum model height at which the relative humidity is at least 75%, shown in red, then we get results that are very close to the observations. In this case, our biases are less than 100 meters. Moving forward, we use carbon monoxide, ozone, and black carbon from the P3 observations to compare against both emission inventories. We see little variation in performance from both inventories in reproducing CO and ozone. This indicates that the emissions of hydrocarbons, which are the ozone precursors, are very similar between these inventories. However, when comparing black carbon, you see that QFET tend to overestimate the concentrations by around 600 nanograms per cubic meter. On the other hand, our custom emissions slightly underestimate black carbon, but at the same time, our emissions show a larger correlation with observation. This can be explained by the differences in generated emission fluxes from each inventory. Here you see a time series of hourly total emissions for organic carbon, black carbon, carbon monoxide, and sulfur dioxide for the first 20 days of September. The orange colors represent the QFED emissions, and in blue are our custom VIRS-based emissions. We also included fin emissions in green, just to see how our inventory deviates from these two widely used inventories. It is evident that VIRS BBEM generates less emissions than QFED in all these four species, but with smaller differences when compared to fin, even though fin emissions are generated using a bottom-up approach. Overall, our custom emissions fall between QFET and fin. To have a better appreciation of the whole picture in our domain, we compare it against aerosol optical thickness at 550 nanometers from MODIS Terra and Aqua. So here you see a composite of the first 15 days of September 2016. The gray areas are data gaps because we filtered cloudy areas. Because of this, we do not have data every day in all grid points. So this figure shows the significance of our data. You can see that over the ocean, we have no more than 5 days weighted in our average, but over land, we have a decent amount of data. The other plots show the result from our model sensitivity simulations and the respective biases in the bottom. It is easy to see that QFET overestimates the AOD with biases above 0.5 in the main core of the plume. This is possibly due to an overestimation of aerosol species in this inventory, as we saw before. Our custom emissions have a better performance over land with overall biases of around 0.1, but reproduces the plume transport farther west than in reality. Another important aspect is that our VIRS-based emissions slightly underestimate the smoke over land. Finally, our emissions with plume rise turned off showed little difference than when it's turned on, but it shows smaller biases in the west side of the domain. This may indicate that the plume rise is overestimating the injection heights of the smoke plumes, so the emissions are subject to the mid-level jet that transport the smoke farther west. To analyze better the impacts of the plume rise in our domain, here you see the estimated smoke plume top for both sensitivity simulations, when we use plume rise and when we don't. We used a threshold of 200 nanograms per cubic meter to define the smoke layer. Over the continent, the smoke reaches altitudes of up to 6 kilometers when we use plume rise and around 5 kilometers when we don't. This 1 kilometer deviation can determine the extent of transport that the smoke is going to suffer by the strong winds of the jet. In the bottom, you see a cross-section of black carbon at 10 degrees south. Here is visible that over land the smoke reaches altitudes above 6 kilometers when we use plume rise, but this does not happen when we don't. However, when plume rise is turned off, we have higher concentration of smoke over the land surface. Unfortunately, none of the flights conducted during oracles were over land to evaluate if this is accurate. The fact that the simulation with plume rise off performs slightly better in reproducing the AOD as we saw before may indicate that plume rise may be overestimating the injection heights in this region. However, these differences are very little. This does not surprise us, since the fires here are small and the boundary layer over land develops very high during the day, reaching up to 4 kilometers, which in theory does not make necessary the use of plume rise, since the emissions are being mixed within this layer anyways. We also compared against the HSRL data on board of the ER2 aircraft on September 12th. Here you can see the track of this flight. On the left, we are showing the backscatter coefficient and the uncertainty of this data. All data gaps shown in black are because of cloud filtering. In the model, we do not have backscatter, but we do have extinction coefficient, which can give an idea of the smoke. Here in the bottom, you see the relative humidity from the model across the flight track to give an idea of the uncertainty of the extinction coefficient. In general, the model reproduces the smoke shape very well, but of course, it does not reproduce the small details, since the model has a coarser vertical grid compared with the LiDAR. We ran our simulations just until September 15th, but we did an effort to run for an additional day and be able to compare against the second ER2 flight conducted on September 16th. Results were very similar to our previous slide. The model, in general, is able to reproduce the shape and thickness of the plume very well in both days. The cross-sections here show a summary of the conditions during the first 15 days of September. The smoke plume over land and its transport over the ocean is clearly visible due to the mid-level jet. These are our conclusions. We developed our emission inventory based on various thermal anomaly detections and conducted simulations with WRF-Chem to compare it against QFET. Results show that both inventories reproduce the trace gases accurately, but QFET tend to overestimate aerosols. We also evaluated the use of plume rise process in this region, and we found out that results are slightly changed when plume rise is turned off, but probably it is not necessary to use it in this region due to the nature of the fires. We still can further develop a biomass burning emission model by including a method to account for undetected fires covered by clouds. Also, we are investigating the uncertainties of various fire radiative power retrievals. Finally, we plan to run our simulations for the 3 years of oracles to have more robust results. Thanks for your attention. If you have questions, please email me, and I hope to see you on Wednesday at 1 p.m. Eastern.